All right, let's work our way through some of these multiple choice questions. This is the algebra-based questions. However, we're going to hit both the algebra and the AP as per your request. We have two sound sources, two speakers, S1 and S2. One of these is emitting high-pitched sound, 1000 hertz. The other one is emitting sound that's half that pitch, relatively low pitch. How does the speed of the first wave compare to the speed of the second wave? This is a tricky question because most people would say the high frequency wave travels faster than the low frequency, but actually the answer is the same because the V of sound depends, the velocity of sound depends on what material it's traveling through, and both the 1000 and 500 hertz waves are traveling in air, which will be they're about 340 meters per second depending on the temperature. That's a trick question right off the bat. The speed of the waves are going to be the same. Don't worry about it. We stated before that sound will travel differently in different types of materials, air, water versus steel. And we said it travels fastest in steel as compared to air, water being in the middle. So velocity in air is less than that of water, is less than that of steel. So steel is going to be the greatest velocity, and air will be the lowest velocity. So E is the correct answer. Again, you can test yourself and then use this feedback. The speed of the wave depends on the medium or the mechanical properties of that. So the question is now, which point oscillates at the highest frequencies? If we look at these points and we measure the distance between the crests and troughs, or the crest and crest, since those distances are all the same, A, B, C, and D will all experience the same frequency. The only way that they would have different frequencies is if the wave spacings were different. So we'll keep moving. The loudness of a sound wave increases with amplitude. So this is a soft sound wave. And this is a loud one. Sorry about that. So this is soft. And over here is loud. And that's the amplitude. The height of the wave is the amplitude. So this is a small amplitude, small positive amplitude, a large positive amplitude, a small negative amplitude, a large negative amplitude. So again, the height of the wave is the volume. Which of these do not change when you go from air into water? And this happens to be the frequency. When you go from one material to another, from air to water, you'll experience what's called refraction. This was not really this question was not covered in the chapter, but we'll have to deal with it. It's something you'll have to know and memorize. The next question states a sound wave resonates in a tube with two open ends. What are the wavelengths of the three lowest resonating frequencies generated in the tube? So what I'll do is to draw this. So I'll draw some lines, and we'll make some, I don't know, some relatively fat lines, fatter than we normally deal with. So I'll draw my first tube, and so that's tube number 1. It's open on one end and the other. And then I'm just going to take and group these, group and dupe. So I have 3 different situations, and this will be, it's getting busy. So we'll just separate these tubes with some doodle in yellow so that it's not too busy. Here's my first tube. Here's my second tube, and here's my third tube. Now, if you recall that these waveforms have to have antinodes at either end, so there's my first possible waveform. These are difficult to draw. Here's my second possible waveform, and these are standing waves in air columns, and so on. And this one's going to be difficult to get right, but we'll try here. Well, almost. Let me just scoot one thing over here a little bit. That's good. And now to draw these waveforms, it's tricky, it takes some experience to do this. we're good to go. We did this earlier together. This one contains 1 2/4 of a wave. So for open ends, 2 times the length, or the wavelength will be 2 times the length divided by the number of antinodes. And this one really has 1 antinode present. So 2 times the length would give me 4/4, 3, 4. So 2L is my first one. This one contains 1, 2, 3, 4/4. So L will be this wavelength. And this one contains 1, 2, 3, 4, 5, 6/4. So 2/3. Oh, I'm sorry. 2/3 of the length will correspond with the wavelength. So let's see if we can find the answer. 2L, check. L, check. And 2/3 L. The answer is B. What would the next wavelength be? Can you predict? Think about that. Let's hold that thought for now. We'll keep going. The lowest frequency in an open tube is 250 Hertz. So that's F. What are the other frequencies that will resonate in the tube? Let's go back a picture and I'll switch colors. This is F. This is how many, so this F contains 2 and 2 wave quarters. This one contains 4 wave quarters. That means it must be twice as frequent. This one contains not 4 but 6, 3 times as many as the first one, so that's 3F. Tubes with open ends will resonate at F, 2F, and 3F. So let's look here. If they state that F is 250, what will 2F be? Oh, that's going to be 500. So that's, oh, that gets rid of everything. The next, so 2F will be 500. What is 3F? 750, which is 3 times the original value. What is 4F? 4 times 250 is 1,000, so that A is the correct answer. I want to remind you that tubes with open ends at both ends will resonate at F, 2F, 3F, and 4F. Guaranteed the next question is going to be one closed end. The lowest frequency? No, it's not. The lowest frequency in open tube is 100 Hertz. What are the following frequencies? Which of the following frequencies will resonate? So that's F. It will also do 2F, which is 200 Hertz. 3F is 300 Hertz. 4F is 400 Hertz. 500, and so on. Whoops, got carried away. 25 is not one of these values. 50 is not one of these values. 150 is not one of these values. Neither is 250. 200 Hertz will be at 2F. So if we look at this bad boy, and they state that the length of the tube is 1 meter, the question is, what is the wavelength? So we have 1, 2, 3, 4 wave quarters. Waves contain 4 parts. If 4/4 of the wave fits in here, the wavelength is 1 meter. How many antinodes are there? 1, 2. Wavelength is 2L divided by N, and N is 2 in this case. So wavelength is 1 meter, the length. 2 over 2 cancels. Lambda wavelength equals L, 1 meter. Let's look at this bad boy. So now what musical note will this thing, or what is the resonating frequency? What is the pitch of this tube, assuming the velocity is 340 meters per second? So we stated previously that the wavelength is 1 meter. Whoa! Let's read 2 meters. And so we know that velocity is lambda times frequency. Frequency is velocity divided by lambda. So 340 meters per second divided by 2 meters will give us 1/2 which are hertz. 340 divided by 2 is 170 hertz. Here's a question for you. If a tube that's 2 meters long sings at a pitch of 170 hertz. A smaller tube that contains the same amount of wave must sing at a, you tell me, if the wavelength goes down, if the wavelength is halved, the frequency must double, so it would be 2 times that amount. Smaller tubes will sing at higher pitches if we're containing this much wave. Longer tubes will sing at lower pitches. Let's read this one. This tube is 6 meters in length. This contains 1, 2, 3, 4, 5, 6 quarters. So one wavelength would be 4/6 of the total length. What is 4/6 of 6? Oh, let's do that. 4/6 of 6 is 4 meters. So lambda is 4 meters. Beautiful. What is the frequency that this will sing at? If the length is 1.5 meters, again, the wavelength will be 4/6 of the total length in this case, because 1, 2, 3, 4. This will correspond with 1 complete wavelength. 4/6 of that total, this being the 5th and the 6th, odd men out here. So 4/6 of the length, 4/6 of 1.5 will be 2 1.5s is 3, 4 1.5s is 6, or R6, so the wavelength is 6/6, 1 meter. So the frequency, oh, how about that? Ruh-roh. V is lambda f. If the wavelength is the wavelength is 1.5 meters, the velocity is 340 meters per second. The frequency will be 340 divided by 1.5. So it's going to be higher than all of these values. We'll get rid of that. And if you get your calculator out and do 340 divided by 1.5, it's going to give you a value. Ruh-roh. Let's double check this. Oh, excuse me, 340 divided by 1. I made a mistake. So let's back it up. We'll ablate my answer. This should read 340 meters per second is equal to 1 meter times f, because lambda, so f is actually, I'm so sorry, f is 340 hertz. So this will sing at 340 vibrations per second. So now we have a tube with one open end. Let's draw that bad boy. Just moving through this. So I have my tube. There's my first part of the tube, second, third part of the tube. So we have open ends. We'll group and dupe. So we have 3. So the question is, what are the 3 lowest frequencies that will do this? And there are 4 quarters of a wave per wavelength. And this bad boy will resonate with nodes, always at this end, because waves will go in, hit, and then bounce out. And in the first case, we will have a node and an antinode. The second case, it will look like that. The third case, it will look like this. Kind of hard to draw. Take some practice. And so on. So now, how many quarters of a wave are present in the first tube? The answer is 1. So lambda will be equal to 4 times the length. How many quarters are present here? 1, 2, 3. So you have 1.3 wavelengths, or rather, if the wavelength is, or excuse me, if you have 3 quarters of a wave, lambda will be 4/3 of the length. So you'd need one more third. This contains 1, 2, 3, 4, 5. So lambda will be not the entire wave, not the entire tube, but 4/5 of that length. E is the correct answer. And again, remember, this one is more frequent. It will be 3 times the frequent. This one is more frequent yet. It contains 5 times as many waveforms, therefore it's 5 times as many quarters, therefore it's 5 times as frequent. As you go in this direction, frequency will increase. So we can sing at, I don't know, if this were 100 hertz, this next frequency will be 300 hertz, and this one would be 500 hertz. It explains why you can bugle at different frequencies without changing the length of the tube. So the lowest frequency for a closed tube, F is 200 hertz. Remember, you're going to resonate at 3F, 5F, 7F, and so on. So 3F would be 600 hertz. 5F would be 5 times 200, 1000 hertz. 7 times 200 or 1400 hertz. A is the answer. If the lowest frequency in a closed tube is 300 hertz, which of the following frequencies will resonate? So remember, this is F. It'll go 3F, 5F, 7F. Let's cover everything here. 9F and so on. 3 300s are 900 hertz. 5 300s are 1500 hertz. 7 300s are 2100 hertz. 9 300s are 2700 hertz. So these are the allowable frequencies that this tube could sing at or resonate at. So let's check our list. Is it 900 hertz on there? Yes, it is. Is 1000 hertz a possible value? Nope. 1200? Nope. 2500? Not going to happen. 3000 hertz? Not on the list. Let's just double check. If we did 11F, 11 threes are 3300 hertz, just to make sure we can get up above our highest value. So these are impossible. How could you resonate at 1000 hertz? What would you need to do to the tube in order to resonate at 1000 hertz? What would the fundamental frequency have to be for the third harmonic to resonate at 1000 hertz? Think about that. What is 3 times some number will give you 1000? That will be about 333 hertz for F. 3F will be, about 999 hertz. So that's an extra. We'll leave it there. What would you have to do to the tube to make it more frequent? The answer is decrease its length. We'll play with that together. 2 sources generate pure tones at 500 and 525. What is the beat frequency? It's simply the difference. It's not likely we would be able to hear that beat frequency because we can only perceive about 10 vibrations per second difference between these. A sound wave resonates in a closed pipe with a length of 3 meters. What is the wavelength? So if this is 3 meters, we contain 1, 2, 3/4 of a wave. So lambda is 4/3 of the length. The length is 3. Lambda is 4 meters. D is the correct answer. So again, remember, you don't have an entire waveform in here. To have an entire waveform, you need 4/4. So you need this much more tube to fit the entire lambda, because I'll draw one complete wavelength, up, down, and then back. So you need more tube than you have wave. So the wavelength is going to be bigger than the tube length, 4/3 of that length. What the next question is, if L is 3.5 meters, what is the wavelength of the wave? This is a tough one. So here is one wavelength. Will the wavelength be more or less than 3.5 meters? The answer is less because it's less than the length. So we have a complete wavelength fitting in there. So we have 1, 2, 3, 4, 5, 6, 7. If the entire tube contains 7 quarters, 4/7 of the length will be equal to lambda. So 4 times 3.5 meters, that's the length, divided by 7. Well, let's get our old calculator out just for fun. Whoa, getting carried away. 4 times 3.5 is 14 divided by 7 is 2. I probably didn't need the calculator to do that, but anyhow. So the answer is 2 meters. So that distance, and again I'll draw it, that distance from there to there corresponds with 2 meters of distance. Let's use a different font, 2 meters. Okay, we're getting close here. What is the resonating frequency of this one? We know velocity is lambda times f. We need to solve for f. We know v, that's given. We need to figure out the wavelength. This is one complete waveform, so the wavelength is going to be less than the total length. We have 1, 2, 3, 4, 5 5/4 of a wave. So lambda will be 4/5 of the total length, and that length will be 2.5 meters. 2 times 2.5 is 5, times 4 is 10, divided by 5 is 2 meters. So we have a wavelength of 2 meters, and the velocity is 340 meters per second. 340 divided by 2 is 170 hertz. So this will sing at 170 hertz. And by the way, this is 5 times the fundamental frequency. This will also sing at 3F and F and 7F and so on. So F, if this is 5F, the fundamental frequency would be 170 hertz divided by 5. It would be 1/5 that original value, and so on. Let's see if they're going to ask that. No, they're not going to. Two sound sources produce waves slightly different frequencies. What happens to the beat frequency if the lowest tone increases and passes the higher tone? What happens to the beat frequency if the frequency of the lowest tone increases and passes the higher tone? Well, the difference between the two frequencies will decrease as they approach each other. So initially they will decrease, and then after the fact they'll go away from each other. They're going to increase. We'll have to demonstrate that together. Again, we'll come back. So again, this was the algebra-based questions, and we're using this to gain or to become more comfortable with the content, and then eventually we'll go back and cover the AP questions. So I'll present the AP questions within another movie.